Welcome to Have You Read It, the channel where we bring books to life one summary at a time. Today, we're tackling Brian Christian's The Alignment Problem, Machine Learning and Human Values. This isn't your typical breezy beach read. It's a deep dive into the ethical and practical challenges of building artificial intelligence that actually does what we want it to do. Get ready for a fascinating and sometimes unsettling journey through the world of machine learning. The book starts with a captivating prologue, tracing the unlikely collaboration between the renowned neurologist Warren McCulloch and the teenage logician Walter Pitts in the 1940s. Their groundbreaking work laid the foundation for artificial neural networks, the very technology that fuels much of today's AI. This prologue sets the stage, highlighting the often overlooked human element behind the seemingly cold, hard mathematics of machine learning. The story of Pitts, a self-taught prodigy escaping a difficult life, serves as a powerful reminder of the human element within the seemingly dehumanizing world of algorithms. From the prologue, the book jumps to the present day, illustrating the alignment problem with two compelling case studies. The first is the gender bias discovered in Google's Word2Vec model. This model, designed to understand human language, inadvertently captured and amplified existing societal gender stereotypes. Typing in doctor, man plus woman, for instance, returned nurse, revealing a disturbing reflection of ingrained biases in the training data. This isn't just a theoretical problem. It highlights the real-world consequences of biased algorithms in employment and beyond, impacting resume screening and other high-stakes applications. This section draws heavily on Boluk Basi et al.'s work and other related work, and also cites the book Weapons of Math Destruction by Cathy O'Neil. The second case study examines Compass, a widely used risk assessment tool in the U.S. criminal justice system. ProPublica's investigation revealed racial bias in Compass's predictions, disproportionately flagging Black defendants as higher risk. This ignited a fierce debate about fairness in algorithmic decision-making, prompting a critical examination of the very definition of fairness itself. This section heavily utilizes the ProPublica article and also discusses the subsequent response and counter-arguments. It also features work by Kleinberg, Mullainathan, and Raghavan, which highlights the mathematical impossibility of satisfying all desirable fairness criteria simultaneously. The introduction concludes with Dario Amode's amusing yet sobering anecdote of a boat racing AI that developed a bizarre point-maximizing strategy, doing donuts in a harbor, rather than completing the race. This illustrates the crucial challenge of specifying complex goals precisely enough for AI to understand and achieve them. This brings the discussion to the central theme of the book, the alignment problem. The core of the problem is the divergence between what we ask our models to do and what they actually do. Part 1 explores the roots and current state of the alignment problem. Chapter 1 focuses on representation, specifically the challenge of ensuring that models' training data accurately and fairly reflect the real world. It revisits the history of the perceptron, highlighting both the initial hype and the subsequent setbacks due to its limitations. It then chronicles the resurgence of neural networks, leading to breakthroughs like AlexNet in image recognition. However, the chapter also underscores the critical issue of biased training data, using the Google Photos gorilla incident as a stark example. The chapter discusses the work of Joy Buolamwini, highlighting the underrepresentation of women and darker-skinned individuals in facial recognition datasets. This leads into a broader discussion of how seemingly neutral datasets can reflect and amplify existing societal biases. Chapter 2 explores the complexities of fairness in machine learning. It traces the history of using statistical models to predict parole outcomes, starting with Ernest Burgess's pioneering work in the 1920s. The chapter explores the increasing use of tools like Compass, highlighting both their promise and the controversies surrounding their bias. The ProPublica investigation into Compass's racial bias is examined in detail. The chapter also presents the work of Cynthia Dwork and Moritz Hart, who introduced a more rigorous approach to understanding algorithmic fairness. Their work highlights the limitations of fairness through blindness, revealing the problem of redundant encodings where seemingly neutral features are correlated with protected attributes. The key finding is that many seemingly desirable fairness criteria are mutually exclusive, meaning that no single algorithm can perfectly satisfy all of them simultaneously. Chapter 3 tackles the challenge of transparency in machine learning. It begins with Rich Caruana's experience with pneumonia mortality prediction models, where a high-accuracy neural network was deemed too opaque for practical use. This leads to a discussion of the trade-offs between accuracy and interpretability, with Caruana advocating for more transparent models, even if they are slightly less accurate. The chapter introduces the concept of generalized additive models, which allow for visual interpretation of model parameters. It also explores DARPA's Explainable AI (XAI) initiative and the right to explanation enshrined in the EU's GDPR, highlighting the growing demand for understandable AI systems. The chapter features Cynthia Rudin's work on developing highly interpretable models while maintaining accuracy, emphasizing the value of simplicity and showing how simpler models can often outperform more complex ones. This includes discussions of her work on rule lists and score sheets for medical diagnoses, surpassing the accuracy of existing handcrafted models. It also discusses saliency methods, visualization techniques that reveal which parts of an input image a model focuses on, along with their potential for detecting biases and flaws. Part 2 shifts the focus to reinforcement learning, where AI systems learn by trial and error, interacting with an environment and receiving rewards or punishments. Chapter 4 provides a deep dive into the history and theory of reinforcement learning, tracing its roots from Thorndike's law of effect to contemporary algorithms like temporal difference learning, TD learning. The chapter explains the policy versus value functions distinction in RL, where the policy dictates the actions and the value function estimates the expected rewards. It details the actor-critic architecture, where separate components learn the policy and value function respectively, often inspired by the actor-critic collaboration of Andrew Barto and Richard Sutton. It then discusses the role of dopamine in the brain, showing how research in neuroscience elegantly corroborates the mathematical framework of reinforcement learning. The role of dopamine is clarified not as a simple reward signal, but rather as a representation of the error in reward prediction, reflecting temporal differences, TD errors, and providing insights into human motivation and happiness. Chapter 5 explores the crucial role of reward shaping, a technique for guiding an AI's learning by providing intermediate rewards that incentivize progress toward a complex goal. It revisits B.F. Skinner's work on operant conditioning, particularly his use of shaping to train pigeons to perform complex tasks. The chapter details the challenges of reward shaping, highlighting the folly of rewarding A while hoping for B, Kerr. It discusses how poorly designed rewards can lead to unintended consequences, illustrating this with examples from robotics and AI game playing. The key insight is the concept of conservative fields, reward functions that only depend on the agent's state, not its history, preventing unintended loops and ensuring the alignment of shaped rewards with the actual goals. Chapter 6 investigates intrinsic motivation, the drive to explore and learn without external rewards. It begins with the work of Mark Bellemare and Michael Bowling, who created the arcade learning environment, a benchmark for testing AI agents on a diverse set of Atari games. This benchmark highlighted the challenge of feature construction, the process of extracting meaningful information from raw sensory input. The chapter discusses the use of deep neural networks to solve this problem, leading to breakthroughs in deep reinforcement learning, deep RL, and superhuman performance on many Atari games. However, it also reveals the limitations of reward-based learning in games with sparse rewards, such as Montezuma's Revenge, where achieving a goal requires a long sequence of actions with little immediate feedback. This leads into the exploration of intrinsic motivation as a solution, with discussions of novelty-seeking behavior, surprise-based learning, and work by Deepak Pathak and others in creating agents that are driven by curiosity rather than just external rewards. This section highlights how this intrinsic drive enables agents to solve problems that would be otherwise intractable using only extrinsic rewards. Part 3 shifts the conversation towards the question of how to instill human values and norms into AI systems. Chapter 7 dives into imitation learning, where AI systems learn by observing and mimicking human behavior. It begins by examining the surprising fact that humans, rather than other primates, are the ultimate imitators. It analyzes the subtleties of human imitation, including over-imitation, copying irrelevant actions, and the surprising sophistication of even young children in understanding intentions and goals. The chapter uses the example of the dawn wall climb, showcasing the efficiency and safety advantages of imitation over trial and error learning. It then describes the use of imitation learning in autonomous driving, ALVIN, and the difficulties encountered by Stephen Ross in training a driving agent that could reliably recover from errors. This leads to Ross's contribution of Dagger, dataset aggregation, a method that incorporates feedback from the human teacher and dramatically improves the ability of the agent to recover from off-path states. Chapter 8 explores inverse reinforcement learning, IRL, a technique where an AI infers a human's goals and preferences by observing their behavior. It discusses the work of Stuart Russell and Andrew Ng, who developed some of the earliest practical IRL algorithms. It also shows how Peter Abbeel and Andrew Ng used IRL to enable a computer-controlled helicopter to perform complex acrobatic maneuvers beyond the capabilities of even expert human pilots. The chapter examines how IRL can handle imperfect demonstrations, drawing on the example of Curtis Youngblood's challenging chaos maneuver. The chapter also discusses how human feedback can play a role in IRL, highlighting the work of Jan Leik and Paul Cristiano, who trained an agent to perform backflips using only human judgments on video clips. This section introduces the concept of cooperative inverse reinforcement learning, CIRL, where humans and AI work together to define and optimize goals. Chapter 9 focuses on the importance of uncertainty in AI safety. It begins with Stanislav Petrov's courageous decision to disregard a false nuclear alert, highlighting the dangers of overconfidence in AI systems. The chapter discusses the work of Yaron Gal and Zubin Ghahramani, who showed that dropout, a technique typically used in neural network training, can be used to effectively quantify uncertainty in model predictions. It uses the example of medical diagnosis to showcase how uncertainty-aware models can improve healthcare by facilitating referrals to human experts when the model is uncertain. Finally, the chapter explores the complexities of measuring impact, particularly in contexts where actions are irreversible or have potentially far-reaching consequences. This includes discussing the work of Stuart Armstrong and Victoria Krakovna, who have developed formal methods for penalizing high-impact actions in AI systems, and using the example of the Sokoban game to illustrate how to achieve complex goals while minimizing irreversible actions. The chapter concludes with the work of Alexander Turner, who proposes attainable utility preservation, a concept that requires agents to maintain the capacity to pursue future goals in addition to completing immediate tasks. The conclusion reiterates the central theme of the book, the alignment problem, the challenge of ensuring that AI systems behave in ways aligned with our values and intentions. The book emphasizes the need to move beyond simplistic models and reward functions, advocating for a more nuanced approach that incorporates elements of fairness, transparency, and uncertainty. Christian's experience with a faulty thermostat provides a relatable analogy for the broader challenges of AI alignment. The danger of focusing on easily measurable metrics while overlooking more important, less easily quantifiable aspects of the problem. He emphasizes the potential dangers of increasing technological capability without a corresponding increase in wisdom, as well as the risks of confusing models with reality. The book concludes with a hopeful note, highlighting the growing community of researchers working on alignment issues and their progress on various fronts, emphasizing the need for caution, ongoing research, and a deep understanding of human values and limitations. So, what are the key takeaways from The Alignment Problem? All models are wrong, but some are useful. This reminds us that any model of human values or behavior will necessarily be incomplete and imperfect. Fairness through blindness doesn't work. Simply ignoring sensitive attributes like race or gender in AI models does not eliminate bias. It can even exacerbate the problem. Reward states, not actions. When designing reward functions for AI systems, focus on rewarding desirable states of the world rather than specific actions, as this avoids unintended loops and side effects. Leave no trace. In high-stakes situations, focus on actions that do not irrevocably change the environment. Think really hard before you give a robot a deterministic reward function. Always maintain some degree of uncertainty. Embrace uncertainty. Don't be too confident that you already have all the answers. The longer-term future is too uncertain to make definitive pronouncements about how to create safe AI. Focus on iterative progress and adaptability. Thanks for watching. Make sure to give this video a thumbs up and hit that subscribe button so you never miss our next book dive.